Okay, so we may start. First of all, as usual, I will announce our next seminar. So next week, we will have a talk from the speaker also from Skolkovo. It will be Ilya Luchnikov, and he will told us about Riemann optimization for quantum technologies. And now our speaker is Jacob Biamonte, also from Skolkovo. And he will talk us about introduction to modern quantum algorithms, optimization, simulation, and machine learning. Actually, this is about his doctoral thesis. Yeah, thank you. Start.
Dear colleagues, thank you very much for hosting this talk. Please feel free to ask questions as I go. As Konstantin has correctly pointed out, the talk roughly follows the doctoral thesis, which I recently have written. And so feedback on that thesis is also quite encouraged. And the slides for the talk and the thesis are available by email request or otherwise. And what I wanted to do today was just kind of discuss, what are the objectives in terms of where are we trying to go with quantum computation? What do we hope to accomplish? And what do we anticipate that we wish to recover from this quantum speedup? And so in order to do that, we have to define some basic notions of quantum complexity theory. And the standard classes to do this are ones that you're probably quite familiar with, this class and this class, regardless of your quantum experience. And this class is maybe less familiar, but it's the idea of a classical algorithm that runs in polynomial time. P is, of course, the class of problems that can be solved or decided if they're decision problems in polynomial time. And NP is the class of problems that you can check in polynomial time. There's a quantum analog of these classes. Okay, the class, BQP is basically the class of main interest for quantum simulation, emulation, etc. This is sort of a class of algorithms which execute with polynomial depth quantum circuits. And then the quantum analog of NP is QMA, which is the class of problems that have an efficient proof. If you're provided the circuit, you can determine if this circuit is accepted or rejected. Where accepted or rejected is if it's a yes instance, it can be verified. And if that particular vector does not correspond to a accepting instance, it will be rejected. So it's a form of decision problem. Now, what we anticipate, so why is everyone building a quantum computer other than it's just fun to do quantum physics experiments, right? So the quantum physics experiments have obviously went forward tremendously from this, but the goal is, okay, the original kind of idea was, oh, well, we can do factorization and we can do discrete log and a whole other host of hidden subgroup problems can be solved in polynomial time, originally by Shor, but also many other papers have worked and developed this further. In addition, you have the idea of search and optimization. These are some kind of polynomial reduction. And also importantly is quantum simulation, quantum chemistry, etc., which is known as polynomial. Now, the best unproven quantum speedups, there should be kind of a line here, and we're kind of looking at it below here. So the best unproven quantum speedups. So these up here are proven, okay, as well as some other ones. There's the zoo, the complexity zoo, by Peter Jordan. Okay, and you can look up all of these different algorithms. So electronic structure, ground state energies. You can simulate one quantum system with another in polynomial time. That's proven to be efficient. It's easy to prove that that's efficient to do. But you can't calculate ground states necessarily. Electronic structure problems are not problems in the sense of computer science. There's no large n limit. The number of electrons is typically fixed for some molecular structure. However, for materials, you end up with larger and larger amount of electrons, and you do want to scale these up eventually. However, for electronic structure of molecules, atoms, etc., the ground state energy should be accessible. one of the arguments that people use is what I call the anthropic argument. Molecules exist in nature that are found in their ground states. Therefore, a physical process exists to put those systems into their ground states. Therefore, we should be able to emulate that process on a quantum computer. And this is sort of a reformulation or sort of a conceptual reformulation of what's called the Deutsch Church Turing thesis, which says that every physical process can be simulated by any other universal computing machine. Okay, and quantum processes are thought to not be in that class under polynomial reduction because of this table, which these are proven to be, the complexity of this is proven, but the speed up over the classical case is either restricted to the oracle setting, which is a black box, or in general, the complexity of certain tasks such as factorization and discrete log is not known. So we're kind of dealing with, let's say, murky water, but there's a lot of phenomenological evidence and there are a lot of proofs, but the proofs are always restricted. Saying something generally about these algorithms and the complexity is very, very difficult to do. And it's not something that needs to be done to cause people to widely accept the fact that these quantum algorithms will outperform the classical case. And most of this evidence is coming from two features. One is that no algorithm exists that is known to exist classically to factor integers in polynomial time or to generally simulate electronic structure in polynomial time. And the other one is with relevance to the oracle model. Are there any questions? Okay, and so of course we have quantum adversarial advantage, which we discussed a little bit at the recent skiing. We went skiing, okay, right as coronavirus was starting, we went skiing. That was like the last thing I remember doing before they locked me inside my house. And large parts of quantum machine learning are also not anticipated to, give exponential speed ups. So to kind of look at the way that we're sort of approaching things inside of the, let's say, the computer science focus group of Skoltech, which the goal of the group is obviously to help kind of do demonstrations of quantum information processing. And so to do that, we're not just working in some bubble, some abstract bubble. We try to apply this to real physical systems. But in order to do it, we obviously can't work with a device physics model, okay? Because that model is too concrete, and the features that we're looking at as quantum programmers are what I would say salient features. They're like structural features, toy models where you can still get out a lot of data. Because if we deal with, the device physics model, it tends to be a little bit too cumbersome for us to really program at that level and have any conceptual insight, okay? So the device physics model is great to look at for small systems. Then we have to make, for a quantum algorithm, we look at some toy model, which gives us some of the features of the device physics model. It's fair enough, everyone's doing it. And so the approach that we take, at least for these slides and the approach that I take in my course and the approach of the thesis, is to think of this abstract model that is roughly inspired by, let's say, Google and IBM. The optical waveguide model would be close to the circuit model, but doesn't necessarily have a Hamiltonian in the standard sense, right? You look at this in a propagator picture for somewhat evident reasons. Anyway, so let's go through this. So these are interaction. This could be, for example, sigma z on, let's say, I, sigma z on, let's say, j. Okay, and that could be a tensor product there. So those are some operators. This is your coupling matrix. This is a coefficient, and these are operators. So the support matrix S of this Jij is defined to have the entries which are 0 and 1. So every time this J matrix doesn't have 0 as an entry, up to some, you could have a cutoff if you want. So every time this thing is above epsilon on the 1 norm away from 0, then you have a cutoff, and then you put a 1 in the entry of its coupling matrix. So it's just an interaction graph of your Hamiltonian. And this is the interaction graph of H and it's a symmetric adjacency matrix for Hermitian H. Are there any questions about the model? So this is like, we're assuming a physical system that has a perfectly tunable version of this Hamiltonian. Now, what we do is we think of these as qubits. Okay, so we have, let's say, 5 qubits here. And we turn our Hamiltonian on in slices of non-commuting terms. So this could be the interaction terms that commute with each other, if they commute with each other. And let's assume that, for example, these are ZZ interactions, ZZ, etc. Then we could have like local, let's say, sigma X, a sigma Y, okay, etc., etc., etc. And then we sort of cycle this thing back and forth. And it goes on forever. And this is how the quantum supremacy demonstration circuits worked. This is what's called the hardware efficient ansatz. So it just relies on this natural connectivity graph. Time here is going up on the page. So this is time. And you're just looking at different layers of non-commuting things. This graph obviously gives rise to kind of a quantum circuit diagram, okay, which you can just draw as a standard quantum circuit where you have your interaction gates, then you have your local gates. We'll do that in the next slide. And you keep going and you sequence these back and forth. Now, the first thing to notice is that these QAOA sequences, these VQE sequences, etc., are similar to this. This is called the hardware efficient ansatz, HEA. This has been done in the IBM experiment. They were kind of the first ones to sort of use this for quantum chemistry. They had good results back like a couple of years ago. This was actually in Nature. There's other papers now coming out that are using various versions of this. The Google Quantum Computational Advantage work. If I say supremacy, I feel like someone's going to jump out of the bushes and hit me with a stick. I'm not trying to offend anybody, but that's what it is. And so, again, this is, let's say, the first, this is a layer of interaction. Okay, this is a layer of local gates, and these things will be sequenced together. Now, if the sequence is long enough, these things can become universal. Actually, the way that that's proven, okay, by Seth Lloyd and others have proven this in other settings, is what they do is they show, oh yeah, by the way, you can realize a universal gate set on each layer, okay? And so then you take a quantum circuit and you can simulate these gates as it gets very, very long. However, when this ansatz is short, no one knows what is the expressibility of these ansatz in general. So in other words, let's say that I have 5 layers on 50 qubits. How much of my Hilbert space can I actually occupy with that? Do I need very, very deep circuits to get my whole Hilbert space or not? What is the computational capacity of a low depth ansatz? Does everyone understand that question? So this is a big question for my group, but also other groups. People are very, very interested in this simple sounding question. It's actually hard to answer. Now, one of the ways that you can answer it, one of the things that we can say is this.
Excuse me, this is a question from Stas.
Oh, okay.
Jacob, does the connectivity of the qubits inside this layer affect the universality condition somehow?
They do, and it's in a tricky way. And in Seth Lloyd's proof, the geometry was assumed to be a straight line. And the proof that we redid kind of his proof and sort of more formalized it, made it a little bit more technical. We assumed kind of various geometries using these like things that are called like non-forcing graphs. And yeah, the geometry does actually play quite an interesting role. Computationally, remember, being completely universal means that you can emulate you can emulate any quantum circuit with this model, okay? That is kind of where the proofs are. And so yeah, the connectivity absolutely will do it. But the other thing that's interesting about the connectivity is to saturate your bipartite entanglement entropies, it depends on the connectivity of the graph. So Google's Sycamore versus IBM's chip, whichever one it is, versus Rigetti's chip, They all have a different topological structure. They all make a different hardware efficient ansatz. So the question we're going to answer as part of the thesis, very small part of the thesis, but a fun part of the thesis. A question we're going to answer is, well, what if we want to create maximally entangled bipartite states across any partition? How do we do that? How deep does the circuit have to be? Does that answer your question? Probably not. It's kind of a terrible talk. I admit this. I do my best. I put together slides. I try. So just keep asking questions. And we can also, after this is over, I don't want to torture the average person in the audience too much because they probably just are doing this to check a box and say, oh, I participated. But afterwards, I'm happy to discuss further with those that are extra interested. Let's say it like that.
Can I ask one question? Is this
Yes, sure.
Okay, so one thing we heard from John Martinez, the public talk is they were amazed by the fact that their machine doesn't bring any strong error, even they scale their qubits level to the level of above 50. And they said all the errors they are facing is basically 1 qubit error and 2 qubit error. Is your question related to what they have discovered, or?
Well, regretfully, and I have to say this in all honesty, basically haven't added much noise to these models yet. I used to work a lot with open systems many years ago. We want to do that. It's one of the things on the kind of agenda to do it. We take a model and we add more and more pieces to it as we study it, right? It's typical for most people that are doing, let's say, theory. We mostly have considered, let's say, closed systems. We have a couple of models. I mean, in the paper we're working on with Stas right now and Oksana, we have a couple of, we have open systems models and stuff, but we're basically considering, and this is actually what the experiments are actually doing today, because we don't have error correction. We consider how many rounds of the hardware efficient ansatz can we do and still maintain good fidelities. So for example, in Google's recent Sycamore data, they were able to do up to 5 layers in QAOA, 5-level QAOA, which means mixer, then problem Hamiltonian. They could do that 5 times. And as Akshay and Philathong, these excellent people that work in the lab at Skolkovo with me, as they will tell you, in practice, they were able to do 5 layers experimentally, but the noise was so high above 3 that they actually only could use 3 to give any type of meaningful data. So right now, the state of the art is about 3 layers of this thing on an algorithm, and much more if they want to do random sampling, which is where the quantum adversarial advantage benchmarks, AKA quantum supremacy, which has now been banned. You're not allowed to say quantum supremacy anymore because it's racist, apparently.
Right. So do you mean it's algorithm specific? So for example, in Google's this quantum advantage, I prefer to say that word, in this Google quantum advantage experiment, is it due to they use a random sampling circuit that relies less to the multi-qubit noise, such that demonstrates this advantage?
I don't know what your question is exactly. Can you rephrase that? I'm sorry.
Okay, so as far as I understood from what Google last year announced, the reason they can do the quantum advantage experiment is because they are not limited by the multi-qubit errors. What limits them is single qubit operation and 2-qubit operation. That's what I understand from their work. And my question to you is, are you trying to design some algorithm which is only limited by this 1 or few qubits operation error?
No, we're not trying to do that.
Okay.
But I like I like the sound of it. I'm not.
So you were just mentioning that most of your group's effort is working on, for example, this bipartite rank. and this is something leads me to the perhaps misconception about your
No.
about your statement.
We're not, okay. So we're working on, okay, so what we're working on is we'd like to understand the epsilon neighborhood of the accessible state space that can be created by the hardware efficient ansatz as a function of depth. That's a major open problem, and you probably need to use algebraic geometry to solve that. We're working on this type of stuff. That's a major open problem. We're studying this in many different ways, okay? What can we actually definitively say? Well, one thing we can say, which I teach in my course, and I mean, it's part of some of our papers, it's kind of a cute trick, which you guys can go home and say, hey, you know, this is a cute trick, I should know this trick. It's kind of like applying the area law from tensor networks kind of backwards. And we can say a little bit about that, but it's, you know, this is already a result that I can kind of show. This is a tool that you can take away from the talk, and you can basically go and do it. So we're, you know, the effort of the group is maybe a little bit different than this specific talk today. Okay.
Sure. All right. So yeah, maybe I just saw the current slides showing on the screen, and that's one of my questions. Maybe we can discuss it after talk.
I would love to actually. We would like to actually work. We also have other projects that are going on about QAOA, for example, being realized with Stas and Sergey Kulik, Oksana, etc. But it's not the purpose of today's talk. So
okay.
The thing that we can. So here's the question: we don't know about the epsilon neighborhood of this hardware efficient ansatz as a function of depth. But what we do know, I can show you right now. It's quite easy to prove. We can already say that there's a lower bound to maybe maximize bipartite rank. Which is interesting because that lower bound depends on the interaction graph of the processor that we're dealing with. Now, it's a little bit different with the optical waveguide stuff. You would think prima facie, but actually it's not. Your circuits actually can be written down in the same exact way, and you could look at this and you can say, well, how deep does my circuit have to be to maybe saturate bipartite rank? So to do that, we work. Bipartite rank is the Schmidt number, the number of non-zero singular values across any reduced bipartite density state, okay, of n qubits. So you chop it in half and you say, okay, the bipartite rank is just the number of, there could be some cutoff, and you can just say, okay, how many singular values are relevant? And rank provides an upper bound on bipartite entanglement that a quantum state can support. A rank K state has at most log 2 K E bits of entanglement. So an E bit is the amount of entanglement in one Bell state, irrespective of the measure used. So we're working, it's kind of like a unit transformation. So we're working in unit, we're working without units. Okay, we're working with E bits or our unit, but it's irrespective. Sorry, we're working without respect to a measure. We're working with respect to any measure. So it's normalized with respect to that.
Yeah. So does dimensionality helps in this case?
What's that?
Does dimensionality help in this case? So if you increase the dimensionality of each, for example, particle carries.
So, well, not for the purposes here, we're assuming everything's a qubit.
Okay.
But in general, if we could get higher dimensional qubits like qtrits, qdits, whatever you want to call it, we would be very happy about that. So if you could, for example, with your trapped atoms, if you could realize a qtrit for us, we'd be very happy if you could do that.
Yeah, so that's a very interesting question. Yeah, so we can discuss that later. Thank you.
Yes, let's go forward. Just short questions, short answers during the talk, and the discussion after, please.
An E-bit is the unit of entanglement contained in a maximally entangled 2-qubit Bell state. So a quantum state with q E-bits of entanglement quantified by any entanglement measure contains the same amount of entanglement in that measure as q Bell states. Okay, so obviously, this can increase with the size of the state space. And if a task requires R bits, it can be done with R or more Bell states, but never with fewer. Maximally entangled states in the space CD cross CD have log 2 D bits of entanglement. So here is what I would call like the quantum circuit combinatorial area law. Very, very simple, okay? Let me cut this. If I cut this right here, what's the maximal number of bits in the bipartition? So I have two density matrices. Let's say, for example, I take this and I take two density matrices out of this. A density matrix from this side over here and a density matrix from this side over here. Well, you look at this thing right here, the minimum is the cut of n over 2, and C is the number of wires you cut, 1, 2, okay? So this minimum is 2, okay? What if I had another gate here? What if I had another gate across here? For example, what if I had a gate here? Well, then I'd cut 3 wires, C would become 3, but still the minimum is 2 and 2, so it's still 2, right? So in principle, you don't need another gate here in principle. The minimal depth circuit that might maximize the number of bits is what is called kind of a balanced circuit, in the sense that the depth across any cut is going to be at least as many as half the number of qubits. Does that make sense?
Yes.
Good. So when we talk about low depth, we define low depth as kind of, this is like the entanglement, this is like what I call like the bipartite threshold. So if you're underneath that, you're not saturating, you cannot saturate bipartite entanglement. Above that, you can, but this is not a bound, this is not saying that you are. This is just saying that you cannot if it's less than that. So it's a very nice trick, actually, guys. It's a very, very nice trick. So an example is the depth of the hardware efficient ansats on each of these grids to be able to get bipartite entanglement saturation scales differently for each grid. And for Rigetti, I mean, Rigetti, they sort of put together these, they put together this like hexagonal things, they piece these together, et cetera, et cetera. And so it has a different kind of scaling coefficient for that. So they all scale a little bit differently, and I think that's very interesting. And so going back to the ion system, where they have a lot of interactions that are possible and they have to turn them off, it's actually very different than the case of superconducting circuits. And the case of waveguides and optics, you guys are basically building a real quantum circuit, and you can think, well, how? I realize that you guys have recently done some universality proofs by saying, look, if we have this type of structure with these gates, and we put this together, we can make any transformation from any vector A to any vector B inside of your Hilbert space, right? Well, there's also a depth where you say, if let's say I'm not able to realize experimentally these very, very long circuits, let's say I'm only able to do, let's say 10 layers. Well, how many qubits am I emulating, right? Will I actually max out my Could I actually max out my bipartite entanglement correlation? So it's interesting. It has very clear experimental consequences. Would you agree with that statement?
Yes, I would. And I have a question. So looking at these graphs in general, it seems like better connectivity means lower depth circuits to saturate bipartite entanglement. Is that true?
Yeah, phenomenologically or empirically, that statement seems to be observed, yes.
So if we, for example, have an all-to-all connectivity, what the scaling will be?
Well, all-to-all connectivity would basically, you wouldn't even need to have all the gates to get it. It would actually be shorter.
So it's even shorter.
So all-to-all connectivity would be like the best thing you could have, but of course that doesn't scale very well. I mean, to physically build it. So let me, we're about 35 minutes into the talk. Normally the talk goes for an hour, right?
Yeah.
Okay. So this, just to conclude this segment, this is a tool. It does apply to optical systems by just writing down the circuit you're trying to realize. And you can look at the partitions of that circuit. You could say, look, how many C0 gates am I realizing in that circuit? Okay, how many qubits am I realizing? You can use this area law, this kind of inverted version of the area law, the combinatorial quantum circuit area law, and you could determine if the experiment you're demonstrating could potentially max out bipartite entanglement, right? And you can also show that it does have a deficit that it could not if your circuit is below some critical depth. So that's the purpose of this. I think it's a good educational observation, and it's kind of a cute tool that you can kind of stick in your back pocket and sort of use when you're dealing with NISC circuits. So the talk will kind of conclude. We'll kind of go into, and this is actually good because we're working on some experimental stuff related to this right now, and we can talk to Stas, everyone who's interested, and we can kind of talk about this. So these guys are actually, to give you an idea of how horrible their lives are, they're actually in my kitchen right now working. So they're down, they probably hear me downstairs speaking, and they probably don't like it. But anyway, so these guys are graduate students in the lab, and we're working on kind of our follow-up right now, where we go through this Google data and we apply our theory to this, and we apply our analysis methods to this, and we kind of shake it around, and we sort of pan out some nice little flakes of gold out of their analysis that they didn't see. So this is coming soon. We're very excited about that. Okay, so what is QAOA? Okay, quantum approximate optimization algorithm. Okay, and the way that this works is you have some tunable quantum circuit that is parameterized by these real parameters, and it acts on some easy to prepare initial state. All right, so for example, you just prepare some modes, you send in your photonics, that's your initial state, then you have a circuit where all the parameters are tunable, and you can adjust these, and you can run this multiple times, and you can estimate some observables in each run. Okay, and what you would like to calculate, for example, is the expected value of some Hamiltonian. So how would you do that? Well, you would prepare a state, then you would make measurements at the end of that, and from those measurements you would calculate the objective function in the language of computing, and that objective function could be, for example, the expected value of a Hamiltonian, so it could give you some energy. It'll assign some energy value to your state. Now, the critically important part is that in modern quantum algorithms, in the variational approach, which we will discuss in some detail, the Hamiltonian can be emulated through the measurement process. So in other words, I don't have to realize the Hamiltonian as a sequence of gates. Why? Well, here's why. So let's say, for example, your Hamiltonian is, let's say, Z1, Z2 plus 1/2 X1, X2. Of course, this is a 2-qubit system. This means that there's a poly Z matrix acting on the first and second qubit, poly X matrix acting on the first and second qubit. This is your Hamiltonian H. So the expected value of this is just a sum of expected values, right? So if I take the expected value, let me go back here. If I take the expected value of this, I end up with these expected values. I can calculate this one, and I can calculate this one by just measuring in the X basis, right? The Born rule. So it's kind of a cute little trick. Oftentimes with this quantum computer science stuff, some of these tricks are really quite elementary, but get a lot of traction. And it might not be how you think of it at first, but it works. And here's the thing. You can calculate all of these separately, which what does it do? It avoids having to emulate these non-commuting terms to make a big gate sequence and to do this kind of crazy, this crazy stuff with lots of overhead. So going a little bit further, we can sort of skip over this, but the point is this. If you give me some waveguides with some tunable parameters, okay? The variational state space is the space that is mapped out by tuning those parameters to all possible assignments. So if we're trying to minimize a Hamiltonian, it has to be done with respect to the ground states that you can actually prepare. Okay, so that's the space that we can search through, and we can calculate our objective function with respect to all the states in that space. Now, there could be a high number of states and you're not able to calculate it with respect to all of them, so you use gradient descent or some other methods to narrow down your search so you can find something that gives you a good minimum where, you know, this is part of the ansatz, which, you know, you will use to create your candidate solution. And so the objective functions that you want to calculate should have a number of terms that is polynomial in the size of your problem. Why is that? Well, otherwise it would automatically blow up and be exponential, okay? Despite that seemingly obvious statement, it turns out that there's many papers on variational algorithms where they did not consider that facet. And there are some that they have now. It's more recent. Now, just to kind of give a good example of this, to say one more time, okay, we already talked about what this is. We prepare some family of states that we can sort of vary over. Depending on your system, you might want to describe that like this. And an interesting connection between variational algorithms and this optimal control can be made by, you know, allowing the quantum computer to sort of optimize itself instead of having to simulate this using optimal control. It's very important, actually. And so we define, you know, going back to this language of complexity, we say that this objective function accepts an input if we get the objective function to evaluate less than some parameter delta. Okay? So, for example, if I give you a problem and I say that the problem, if you calculate this problem, if you calculate the objective function corresponding to this problem instance, the objective function will have 0 energy when you solve the problem instance. Okay? And if I give you the promise that there's a gap in the problem, the Hamiltonian, that has at least energy delta, then this starts to make sense. If the problem is gapped with a non-degenerate ground state, and I can get an approximation of my objective function, which is the energy, and that's less than delta, then obviously, and this is formally proven, obviously this will necessarily have overlap with the ground state, right? If you get energy less than delta, the gap is delta, there's a non, you know, it works. So efficiently computable objective function examples, all right? Energy is the one, you know, chemical Hamiltonians are another one. Calculating generally the expected value of some big Hamiltonian. Okay, we talked about this a little bit, so the slides are slightly out of order. And going a little bit further, let's look at the k-satisfiability problem. Okay, are there any questions first about sort of where we are with this, right? So we introduced first, in the first part of the talk, we introduced the circuit that we're trying to build. And it's similar to what you guys are doing with your optical system. You could make an optical circuit. It wouldn't have the same, you know, round robin pattern, or maybe it would. Okay, you could interact your system differently. Fine. You're given this circuit, you build this circuit, you prototype this circuit. The circuit exists, the quantum circuit exists, and you can stick different photons in it as initial states. Done. And you can tune the parameters of this circuit. Then you can make measurements, and you can post-select with the, you know, you can post-select these measurements, and you can emulate whatever measurement operation you want. So that was the first part of the talk, and what we showed is that if the circuit has less than some depth, it cannot saturate bipartite entanglement. The second part of the talk, we said, okay, what types of things can you calculate with these circuits, and how does that calculation go? And so what we said is, we said, okay, look, you can calculate objective functions which are related to expected value of operators. And these operators are Hamiltonian matrices. Now, in this part of the talk, we're going to show K-satisfiability, which can be embedded into one of these Hamiltonians. So in other words, I can now prepare states, I can measure the satisfiability Hamiltonian, and I can adjust my circuit to minimize this Hamiltonian. It's clear. And satisfiability, the K means that you have K variables in each clause. The clause is a bunch of ORs of variables, and they're all conjuncted together, they're multiplied together. So one example could be, let's say, X or Y or Z. This is 3 variables, and let's say 1, 2, 3, and then you can AND it, which is like a multiplication. Let's say X, 2, any variable you want, A4, or Z, 3 again for some reason, et cetera, et cetera. So this would be an example of 3 sat with 2 clauses. This is called a clause, and the K in front of it is just the number of variables. And we let a K-sat instance consist of M clauses over N Boolean variables, and the clause density of a random instance is defined by this simple fraction. Are there questions about that? We can do an example of that if you guys want. SAT instances are embedded into Hamiltonians. So I can, as I mentioned, I can make a sum over projectors, and I can embed this into an Ising-like model. 3 sat, 2 sat. The decision version of 3 sat is NP complete. The decision version of 2 sat is in P. Okay. Horn sat is P complete. By the way, this is another discussion, but the minimization version of 2 sat is NP hard, as is the minimization version of 3 sat. So we typically consider minimization of 2-body Hamiltonians, or equivalently in the language of complexity, 3-body Hamiltonians with respect to the Ising model. Now, unsatisfiable assignments are penalized with at least 1 unit of energy. So in other words, if I satisfy this, if the instance is satisfiable, it will have a 0 eigenvector, okay, or an eigenvector corresponding to 0 energy. And for every eigenvector that is not the satisfying eigenvector, the energy will be at least 1. And the instance will not have an eigenvalue of 0 if it's not satisfiable. Okay, and so the goal is now, we're going to take some very specific, we're going to switch, and we're not going to use the hardware efficient ansats. We're going to modify this a little bit, and we're going to go into this QAOA stuff, and we're going to use a quantum algorithm to realize this type of minimization. So now we prepare using a circuit, we prepare this using a circuit, we prepare this using some measurement, depending on how we're doing this. In your guys' case, you'd have to realize this in a gate sequence, which is difficult for QAOA. And there you have it. And so in the standard QAOA and in the gate model, what they do is they realize a sequence of these gates where this is the mixing Hamiltonian called the mixer, and this is the problem Hamiltonian, so the HSAT. Are there questions about that? All right, so therefore, when I go down and I talk to you guys and I'm like, hey, let's build this experimentally, you're not allowed to ask me questions later. Because I'll be like, hey, remember in my talk when everyone was asleep and I was like, hey, are there any questions? And no one was awake to hear me say it? Anyway, but if we're going to do this in optics, we'll change it a little bit because it's a little bit more. So optics is more suited, I'd say, towards VQE. QAOA, you have to realize this you do have to realize this Hamiltonian in the gates, but the Hamiltonian is using diagonal operators only in this case. So going a little bit further, what we found was, so this is the actual minimum energy that you're actually trying to calculate. This is what you actually get out of the algorithm. And we're calling this delta, not to be confused with the gap, although it is kind of, you can think of it sort of as a deficit. That's what we call it, as a deficit. And for a short depth circuit, you're obvious, can you solve every problem instance with a short depth circuit? Of course, the answer is no. The circuit depth should scale, according to Grover's algorithm, exponentially. And what we found is, the finding was very specific. It says that the depth of the circuit needed to make an approximation scales with the problem density. Okay, so the order parameter is density. So we've kind of discovered an order parameter, if you can think of it that way in the language of condensed matter. And we danced a bunch of computer science stuff around that, and we sort of published that in physical review letters. And you can kind of see what's happening. So the clause density is just the M, the number of clauses, to N, okay? And this is how good the approximation is, right? And you'll notice at this, right where this phase transition is expected from min 2 sat, the easy hard min 2 sat phase transition is right around when the graph of your problem becomes sort of fully connected. The approximations start to get worse, and it sort of behaves logistically according to this finite interval that we're observing it. This we call a reachability deficit, and that's kind of one of the findings. And so sort of the conclusion, and because it's been quite long, I do have many more slides, by the way. I actually enjoy doing this, so we could really do this all day, but you guys probably don't want that. So the conclusion is the performance of QAOA exhibits strong dependence on the density of the problem instance. The implication is that this provides the first known heuristic and the first general limiting feature of the algorithm. Okay, there were these barren plateaus that were also studied, but this is quite a bit different. The barren plateaus, at least in their initial format, they were done quite abstractly in some kind of large number limit. Now we're looking at random matrix theory to be able to calculate these. There's also some good groups in Los Alamos, et cetera, that are also working on related topics. And so the work was published. This part of the paper was, this part of the thesis was published in the physical review letters. And there's a few chapters in the thesis that kind of go over this in, let's say, very good details. The stuff that I presented today would be, I think, maybe 2 chapters of the thesis. I think there's 5 or 6 chapters. And so, yeah, I think there's probably 6 chapters. And so this is kind of, a portion of the thesis. It's not all of the thesis. We can discuss more of the thesis later, but this is an important part, and it's also a valid part for MSU's interest, because of the fact that there's ongoing demonstrations inside the Russian Federation, inside Moscow, that are geared towards realizing quantum approximate optimization. And so if there's any questions, I think now would be a good time. We have about 7 minutes for questions, and then we can go on into more specialized stuff and maybe keep going a bit. Did we lose our host, by the way?
Yeah, it seems like Kostya is somewhere.
Well,
disconnected.
Computer has crashed.
Okay, I see. Okay, then I will be a host for Kostya while he's away. So I think Philathong Ma has a question. So please.
Yes.
Okay. Thank you, Jacob, for this nice talk on the introduction of the algorithm, specifically on the quantum approximate optimization. So you mentioned that you considered some specific realization with optics. Can you elaborate a bit more on how to realize, for example, a scalable QAOA algorithm with optics?
Okay,
and
but
second,
let me say this before we go down that path so far. I can do it. put it on YouTube, it's a very bad idea, because I would say that the group, Sergey and Stas and myself, and we're all working on this kind of together as a big team. And we have some tricks that are not really in the literature, and it's enabling us to be able to do this. And so we're working quite hard. So if we put it on YouTube before it's published, I think it would be a bad idea. However,
Sure.
if we, actually what I think we should probably do is, why don't we have an internal discussion that isn't on YouTube on maybe Friday or next week on Tuesday, just a research discussion, because I wanted to show actually Sergey what we were doing a little bit more, because last time we discussed it, we were up in the mountains in Sochi. So yes, we have a method to realize it, and we're working on it. And yeah, it's
Okay.
not easy. It's not easy though. It's not easy stuff. I mean, this is like cutting edge experiments. So
Sure. And the second question, you also mentioned about VQE. You said VQE probably is more suitable for optics. Is that also undergoing research, or you can say a bit about it?
it is, but I can tell you why very simply. So VQE does not rely on the emulation of the problem Hamiltonian until in the circuit. So what you do is you make in VQE, you have a quantum circuit, you make this big quantum circuit, and that's fine. And then at the end, you make these measurements in the Pauli matrices. Remember when we were talking about that ZZ Hamiltonian, the XX, and you make those local measurements? QAOA, what they do is they do problem Hamiltonian, driver, problem Hamiltonian, driver, problem Hamiltonian, driver. And what they're doing is they're trying to basically optimize the scheduling, the mixing between those two, to transfer into the solution as fast as possible. And so obviously in waveguides, if I say, hey guys, I need you to realize a bunch of ZZ interactions, right? It's possible for you to do that, but it's not as easy as, let's say, in a superconducting circuit, which automatically has, let's say, two magnetic moments or whatever coupling naturally, or in some other Zeeman type of coupling, right? So maybe in your in your Rydberg atoms, in your trapped atoms, because of the fact that there's a Zeeman style interaction, it might be quite good to be able to look at this as a QAOA problem. In this case, I think the answer is quite evident. So I think for waveguides in optics, VQE would, at least on the surface, would appear to be quite a bit easier to realize. Okay, just because you don't have to realize that Hamiltonian. Now, at the same time, if you have one of these Ising models, let's say it's spatial proximity interaction on the in the trapped atoms, then what you could do is you could pulse these different interact with these different spins all with one pulse. Then you could easily simulate QAOA using trapped atoms. So I think that type of experiment, which I don't believe is too dissimilar to the type of work that Mikkel Lukin and the group at Harvard did in, I think, 2017, 2018, that type of experiment, I think, can be very good for trapped atoms. What do you think, Stas?
Okay, thank you.
I agree.
Stas concurs.
Okay, any other questions?
So, Konstantin, should I send you the slides and maybe a copy of the thesis to distribute?
Yes, please.
Okay.
We'll share it on our site.
Can we end the official part of the talk and then maybe go into some unofficial?
Just now, that's one more question from Ranjit Singh, please.
Thank you for your talk. I have two quick questions. The first one is, what about the Hermitian property of Hamiltonian specified in your presentation? So, I see one part of AI and AJ, but I did not see the Hermitian part of that. And the second question, your Hamiltonian looks like very similar to second harmonic generation. But Am I correct in optics?
Okay, so the Hamiltonian is Hermitian, although you could calculate a non-Hermitian objective function if you were going to do some trickery. But for our purposes, it is Hermitian. And you could probably simulate like harmonic oscillators, etc., or you could use a harmonic oscillator Hamiltonian, but it's not the one that I'm using. What we were trying to do is we're trying to take the ones that are inspired by, let's say, flux qubits or transmons, which have this sort of interaction, you know, A interaction. A could be ZZ, or it could be some other XY type model. And we're just trying to mimic that. Probably that slide is actually quite confusing, and I should just list the different types of Hamiltonians that exist in the different systems and just get rid of that. But for the purpose of my course, I do that in the lecture, and then I just say, okay, this is the general form of the type of Hamiltonians that we sort of loosely want, and yes, they're Hermitian.
Mm-hmm, mm-hmm.
Yeah,
Okay.
Yeah.
Mm-hmm. And what about this the second harmonic generation? Because it seems to me AI we can interpret like one mode, AJ we can interpret like second mode, and then there is a some generations of frequency generation. So maybe you have some idea of using that Hamiltonian in nonlinear optics?
Well, if we can write down, maybe later, if we can write down sort of the second quantized Hamiltonian or something and sort of take a good close look at that and see what we can actually build, I'd be interested in it. But I definitely wasn't thinking about that when I wrote this down. Okay. I was thinking about, you know, superconducting circuits. So my background is much closer to the superconducting circuits background. I worked on projects on that. So the optics, I think mostly I learned about quantum optics on an airplane with Stas. And then I kind of just guessed the rest. So it's not great, but it's not bad either. So, you know, obviously I've worked on quantum mechanics for a couple days at least. So, you know.
Thank you.
Yeah. Not a very good answer, but something, right?
Okay. Any other questions? Okay, I think in this case we may.
Christy, you're muted.
Sorry, thank you. Okay, I see there are no more questions now, and so we may finish our seminar. Thank you so much for a very interesting talk, Jacob. And okay, see all of you next week in our next seminar.
Thank you.
Thank you for listening, everyone. And if you want to discuss this in more detail or discuss the thesis, I'm obviously quite available to that. But this was, let's say, a condensed version of part of the thesis, and it was sort of the first part of the thesis really to kind of get everybody into the idea. And I hope it was especially useful for graduate students. And it also, I hope that it's continuing to make a better connection between the two groups, because it's very exciting for us to work with you guys. And it's been very fun to kind of learn more about what you guys are doing. And I think that we're getting some momentum now. So this is quite cool. We're actually able to understand each other a little bit. And at first it was quite difficult, but it's getting easier. So thank you guys so much.
Thank you.
They're awesome collaborators. And yeah, I look forward to more discussions. So
bye.
Bye-bye.
Thank you. Bye-bye.